Hello everyone, this is Kalpana here. In this video, we are going to solve the given differential equation. So let's get going. Problem: solve dy by dx into x square y cube plus xy equals to 1. Solution: given differential equation dy by dx into x square y cube plus xy equals to 1. You can write this as x square y cube plus xy equals to 1 by dy by dx. Then x square y cube plus xy equals to dx by dy. So now we have dx by dy equals to x square y cube plus xy. So now bring this xy to LHS, then we'll get dx by dy minus xy equals to x square y cube. Okay. We have dx by dy minus y into x equals to y cube into x square, which is Bernoulli's equation in x and y. See, compare with the Bernoulli's equation. We know that Bernoulli's equation in x and y is dx by dy plus p into x equals to q into x power n, where p and q are either functions of y alone or constants. And here you are having n, right? Where n is a real number such that n is not equals to 0 and n is not equals to 1. Now, by comparing these two equations, we can say that this is a Bernoulli's equation in x and y, right? Also, by comparing these two equations, we'll get p and q, where p equals to minus y and q equals to y cube, which are functions of y alone. Since it does not involve any other variable other than y, so we call p and q as functions of y alone. Now, compare x square with x power n, then you'll get n equals to 2, which is a real number, right? Here n is not equals to 2, either not equals to 2 or neither n is 0 or 1, right? So, this is a Bernoulli's equation in x and y. So, we have reduced the given equation to Bernoulli's equation. Now, what we'll do is we'll simply reduce the Bernoulli's equation to linear form. We know that the standard form of linear equation in x is dx by dy plus p into x equals to q, where p and q are either functions of y alone or constants. Okay. So here, just compare these two equations. We have dx by dy plus some function of y into function of x equals to function of y into function of x square. While coming to RHS part, you have either function of y alone or constant, but you don't have any function of x, right? So it involves, but the Bernoulli's equation was x square. So what we have to do to reduce this equation to linear form, we have to eliminate this x square. So how you can eliminate x square? Simply by taking x square to LHS part, or by multiplying both sides of the equation with 1 by x square, or by dividing both sides of the equation with x square. Okay. Now what we are going to do is we'll bring this x square to LHS. Then we'll get 1 by x square into dx by dy minus y into x by x square equals to y cube. I'll show you in detail. Okay. We are bringing this x square to LHS. Then we'll get 1 by x square times dx by dy minus y into x equals to y cube. Then we'll get 1 by x square into dx by dy minus y into x by x square equals to y square, the same thing you'll get, right? If you multiply both sides of this equation with 1 by x square, then x square gets cancelled and again you'll get the same equation. Fine. Now this becomes 1 by x square into dx by dy minus y into, here 1x gets cancelled, you'll get 1 by x equals to y cube. Now let 1 by x equals to some z. The reduced equation is 1 by x square into dx by dy minus y into 1 by x equals to y cube, right? Now let 1 by x equals to z. Now differentiate on both sides with respect to y. So here we are going to use chain rule to differentiate with respect to y. dz by dy equals to dz by, this is a function of x, right? So it involves differential dx in between. So now let's find derivative of z with respect to x. Z equals to 1 by x. Then differentiate on both sides. See 1 by x in the sense x inverse, right? Then d by dx of z equals to d by dx of x inverse. Simply we are differentiating on both sides with respect to x. Then we'll get dz by dx equals to minus x power minus 1 minus 1. Differentiating x inverse with respect to x. From this we'll get dz by dx equals to minus x power minus 1 is minus 2. You can just write this as minus 1 by x square. Okay. If z equals to 1 by x, if we differentiate both sides with respect to x, then dz, if we differentiate on both sides with respect to y, then we'll get dz with respect to y equals to derivative of z with respect to x, that is minus 1 by x square into derivative of x with respect to y, dx by dy. Okay. Fine. Now coming to the first term, here you are having positive 1 by x square into dx by dy, but we got minus 1 by x square into dx by dy. So what we'll do to eliminate minus is, we'll simply multiply both sides of the equation with minus, then you'll get minus dz by dy equals to 1 by x square into dx by dy, right? So when 1 by x equals to z, then 1 by x square into dx by dy equals to minus dz by dy. Now we can change our equation in terms of z and y. Okay. Replace first term by minus dz by dy minus y into, replace 1 by x by z equals to y cube. See, the quotient of dz by dy is minus 1. So in order to make it to plus 1, what we'll do is we'll simply multiply both sides of the equation with minus. Then we'll get dz by dy plus y into z equals to minus y cube, which is linear equation in z and y. Okay. The standard form of linear equation in z is dz by dy. Z and y is dz by dy plus p into z equals to q, where p and q are either functions of y alone or constants. So by comparing these two equations, we can say that we have reduced the Bernoulli's equation to linear form, or the given equation is reduced to linear form or linear equation in Z and Y, or simply linear in Z. Okay. Again, by comparing these two, we'll get P and Q, where P equals to Y and Q equals to minus Y cube. Again, P and Q are functions of Y alone because it does not involve any other variable other than Y. So we call P and Q as functions of Y alone. Now we'll find the general solution to the given equation by using the general solution to the linear form of this equation, right? That is the general solution of linear in Z equation. So we know that the integrating factor of linear equation in Z and Y is given by integral e power integral P differential dy, and general solution is given by Z into integrating factor equals to integral Q into integrating factor into differential dA by plus C. So now we'll use this formula to find the general solution to the given equation. So before going to general solution, firstly we need to find integrating factor. Integrating factor equals to e power integral P dy, which is equals to e power for P equals to Y dy, equals to e power integral Y dy is Y squared by 2. So our integrating factor is e power Y squared by 2. Now we can find the general solution to the given equation. The general solution to the given equation is Z into integrating factor e power Y squared by 2 equals to integral Q minus Y cube into integrating factor e power Y squared by 2 into dy plus C. Now let Y squared by 2 equals to T. Differentiate on both sides with respect to Y. Then we'll get okay. Simply take the constant separately. Then we'll get derivative of y square with respect to y is 2y, right? Then we'll get 1 by 2 into 2y equals to dt by dy. Here 2 gets cancelled. Then y dy equals to dt. Also from y square by 2 equals to t, you will get y square equals to 2t. Now we'll change this in terms of t. Okay, let's see how we are going to change. Just write this as minus y cube e power y square by 2 into dy plus c. Then z into e power y square by 2 equals to minus integral. You can split y cube as y square into y, and remaining will be as it is. Okay. Again, you can write this as y square into e power y square by 2 into y into dy plus c. Now it's easy to replace y dy by dt, and you can replace y square by 2t, and y square by 2 can be replaced by t. This is equals to minus integral replace y square by 2t into e power replace y square by 2 by t, and now replace y dt, sorry, y dy by dt. Okay, simple. Now is equals to minus 2 into integral t e power t dt plus c. Now we need to evaluate integral t e power t dt using integration by parts formula. Integral u dv equals to uv minus integral v du. Okay. Now consider, see the integrand is of the form polynomial into exponential function. Polynomial function into exponential function, right? T is a polynomial function and e power t is an exponential function. Now take polynomial function as u and the remaining as dv. Okay. Let u equals to t and dv equals to the remaining part e power t into dt. Okay. Now differentiate on both sides with respect to t, then you'll get, okay, from this we'll get du equals to dt and integrate on both sides to get v, then you'll get v equals to e power t. Now apply the formula. This equals to uv, u into v minus integral v into du, for du equals to dt, which is equals to t e power t minus integral e power t dt is e power t, right? Now take e power t common from these two terms, then you'll get e power t times t minus 1 is equals to minus 2 into integral t e power t dt is e power t times t minus 1 plus integral constant c is equals to minus 2 into, now replace t, since t equals to y square by 2, then you'll get e power 2, sorry, minus 2 into e power y square by 2 into y square by 2 minus 1 plus c. Now the reduced equation is minus 2 into e power y square by 2 into y square by 2 minus 1 plus c. Now bring this e power y square by 2 to RHS. Simply take this to RHS, okay? Then you'll get z equals to 1 by e power y square by 2 times the RHS part minus 2 e power y square by 2 times y square by 2 minus 1 plus c, which is equals to minus 2 into e power y square by 2 by e power y square by 2 into y square by 2 minus 1 plus c into 1 by y square by 2, c into 1 by e power y square by 2, right? Equals to, here e power y square by 2 gets cancelled from the first term, you'll get minus 2 times y square by 2 minus 1 plus c into reciprocal of e power y square by 2 can be written as e power minus y square by 2, right? So you can write this as z equals to minus 2 into, take the LCM of these two terms, you'll get 2 as your LCM, in the numerator you'll get y square minus 2 into 1, 2 plus c into e power minus y square by 2. Here 2 gets cancelled and you'll get z equals to minus of y square minus 2 plus c into e power minus y square by 2. Simply you can take this minus inside the brackets, then you get z equals to minus y square plus 2 plus c into e power minus y square by 2. We have, since z equals to 1 by x, so now replace z, then you'll get 1 by x equals to, you can write this as 2 minus y square plus c into e power minus y square by 2. Now take this x to RHS, You'll get 1 equals to x times 2 minus y square plus cx e power minus y square by 2. See here, which completes the problem. So we have seen a problem from Bernoulli's equation in this video. Hope you'll understand. We'll see you in the next video. Until then, bye bye.